Hello! For an upcoming AMOS game, I need to be able to make many rooms for a character to move around in, but I don't want to design them all. So, in this video, we're going to take a look at how maps and mazes can be automatically or procedurally generated, allowing them to be different every single time. Procedurally generated games seem to be all the rage these days, with games like No Man's Sky and Minecraft taking advantage. But the concept has been around a very long time and early rogue type games use them a lot. You probably didn't realise because I didn't mention it, but in my previous game, Hop to the Top, I actually had procedurally generated levels. Each time you played, the code generated a completely different level. But it's not the only procedurally generated thing I've created. Many years ago I was experimenting with procedurally generated clouds to use in a 3D environment. It actually looks quite realistic, and if you adjust the parameters you can even get this to look more like snow. I've included the source code for this in the video description. At the heart of this cloud generator and all these procedurally generated levels is one important function. This function generates some kind of pseudo-random number. But how can a computer generate an infinite, unique sequence of numbers? Well, technically it can't. There are ways to achieve this which have become more important for cryptography, but that's way beyond the scope of this video. We need a basic pseudo-random number generator, and there are many of them. As far as I'm aware, all programming languages include a random number function, and as I'll be using AMOS, this looks like it's covered too. But there's a small problem. All random number generators are initialised with a seed number. If you set this seed number to the same value at the start of your program, then you'll get the exact same sequence of numbers out every time. This can be quite useful. For example, if you wanted to share a level you'd played with someone else, they only need to be given the initial seed value, and they'll get the exact same game. You could also set this random seed to something like the current time, so each time you start the program, you end up with a different set of numbers. AMOS includes the randomise function, which should do this, but it doesn't seem to work correctly. If I set the same seed each time, we get a different value. Even worse, if I reset the seed before each call to the random number generator, I still get different numbers. They should all be identical, so this is clearly broken. This isn't what I want for the game, so we need to implement our own random number function, and it's actually quite simple. They're all based on some kind of mathematical formula, where each time you call the function, the seed is updated for the next time, and there's a lot to choose from. One of the most common is the Linear Congruential Generator, or LCG, created in 1958, and it's widely used by many systems and many languages. It's not amazing, but it is really fast. And the formula for it is really easy too, especially when Wikipedia includes some samples. However, we're too lazy for that, so I asked ChatGPT to write the code for me in AMOS. Yeah, okay, so the code isn't perfect for AMOS, but it does tell us what we need to know. And with this new procedure, we can generate a set of pseudo-random numbers. Rerunning the same seed, we get the same numbers. And if we set the seed to timer, we get different numbers each time. Also, if I set the seed before calling the random number function, we get the same value each time. So that's our source of randomness sorted. Now how about level generation? Well, I want to create levels based on tiles that are 8x8 pixels in size. For the screen resolution I want to use, this gives us a maximum of 40 tiles across and 20 tiles high. I want to create random playable room spaces within this, and I'm going to take a very simple approach. I'm going to start by pointing out our nice random number generator here. Now, the basic algorithm here is we pick an X and Y start position with a random width and height. Then we fill that area as map space. We then call this special calc coverage procedure. This procedure does two things. First, it makes a copy of the current maze but expands each point. It does this by scanning every cell, and if a cell doesn't contain anything but one of the surrounding cells above, below or to the sides does, then it also fills this one. Whilst doing this, it keeps a track of how many cells are actually filled. Then, and here's the most important bit, the code is actually drawing this to the screen, so we can use the fill command on one of the previously drawn cells to change them all to another colour. Seems strange, but now I can perform a quick scan of every single pixel, and any pixel that's still the original colour isn't connected to the rest of the maze, so it can't be reached. So the main program keeps repeating this whole process, adding more and more areas until the number of filled cells is high enough and every cell is joined in some ways to the rest. So let's see that in action. First we add a random box in yellow, then we copy it across, expanding it, and then fill it. Then we add a second box, expand it, then perform the fill again. See how the second one stays red, so we know this area can't be reached from the green bit. Then this gets repeated over and over several times until we end up with a finished solution. Now this is running in WinUAE, and it's set up to be a standard AMIGA 500, and you can see this is very slow, so I'm going to speed up the video so you can see it finishing. Now that's not actually a bad map layout either. Given the speed, I'm going to compile the program to see if it's any faster, and the best part is, if we run this, we'll get the exact same maze. Although if I speed this up again, you'll see it's still very slow. If I change the initial seed, and again I'll speed this up, we get a totally different maze. So that's great so far, and you've probably guessed this is going to be a top-down game, although there's no reason why you couldn't render the final maze in other forms such as isometric. The only thing is, this algorithm is very slow. All that drawing to the screen and painting sure does take some time. So, the first optimisation is to stop using the screen as our maze generator. Sure, it was good for prototyping the algorithm, but we need to switch to a memory-based approach. To do this, we're going to switch the code to using arrays instead. Then we'll change the initial box drawing routine to populate an array. And rather than running the code coverage algorithm checking every box is detected, we'll draw 8 boxes at a time first. This new section of code copies this temporary array to the final maze using the expanding algorithm we used before. We've also had to create our own flood fill algorithm. It looks complex, but it's actually fairly simple. I've created a special array to hold coordinates. And I'll start by seeding that array with the start position, and on the map, set that position to 2. Then, for each loop, we look up a coordinate from that array, we then check above, below, to the left and to the right to see what's there. If any of those values is set to 1, we change it to 2, and then store the new coordinates of this position in our array of points to check. This keeps repeating the process until all the positions have been checked. So, let's run that. You may notice I've added a few commands to temporarily disable multitasking and to track time so we can measure performance. Okay, so 6.74 seconds. Not bad. Let's see that in the compiler. 1.28 seconds. That's great. So that's fairly quick, but in a game like this there are other procedurally generated things happening too. I may add some code to generate some internal walls, with maybe some gates, or random positioning of monsters and bonuses, and this all takes time. So, I'm going to attempt to speed this up further. The other thing is, AMOS arrays actually use quite a lot of RAM. Each element uses 4 bytes, so our maze is consuming currently 3.2 kilobytes, and twice that during generation. Not only do we not need all of that space, if I compare array access to reading a byte with peak, 2 bytes with deek, and 4 bytes with leak, whilst not hugely different, you can see that peak is the fastest, assuming all I need is values between 0 and 255, and the arrays by far are the slowest. So I'm going to remove the arrays and switch to using memory. If our maze is 40 by 20, then we only need 800 bytes to store it, not 3.2k, so that's a big saving too. Now you may be wondering how to store a 2-dimensional array in memory. Well, to do this it's actually quite simple. Imagine we created an array that was 4 columns by 3 rows. Note that here I've put the rows first, not the columns. Also, their values are 2 and 3 rather than 3 and 4, because AMOS arrays start from 0 and go up to and including that number. 3 multiplied by 4 is 12, so we need 12 bytes to store it. We can ask AMOS to reserve some memory for us using the reserve command. One thing to note here is if fast RAM is available, it will use that first, which is great. With our 12 bytes freshly made available to us, we could then say that the first 4 bytes are the first row, the next 4 the second row, and the third 4 bytes the third row. So how do we know where a given array position is in memory? Well, that's really easy. We can simply use this formula. And if we want to reverse this, we can use these formulas. Now I know this seems a little bit more complex, but there's some shortcuts we can use to speed this up too. For example, say we wanted to read from row 1 column 2. Well, this gives us an offset of 6 bytes from the start of the memory bank. AMOS internally performs a calculation very similar to this for the arrays too. But we have one advantage here. If we want to read from the next column along, we just add 1 to the current offset, whereas AMOS has to recalculate that position. The same goes for the position to the left. To go to the position below, we add the width, 4, and the one above, we subtract 4. Being able to access our array in memory like this can be considerably faster. This optimisation is something that AMOS's compiler can't necessarily improve upon with its normal arrays. So, let's go back to our maze generation program and replace all of the arrays with a memory bank. The first difference you'll see is that the arrays have gone and have been replaced by 2 memory banks. The second one, bank 11, I'll be using as a temporary maze storage. Now, over to the level generate procedure. Inside the first loop, the first thing you'll see is a calculation for the memory location where one of the random rectangles will be placed. Then 2 loops are used to populate that memory. Notice that this line skips the location to point to the same column in the row below. Now on to the expanding routine. It works the same as before, but uses the addition of subtraction to gain access to the places left, right, above and below. Much quicker. On to flood fill. Lots of memory access here, and I've still got my array to store all the points we want to check, but this time, instead of storing their X and Y position, we'll literally just store their memory location. We're also going to access this array directly too, as we'll be moving backwards and forwards along it one position at a time. Note that when we change its position, we increase or decrease by 4. Remember, each element in an AMOS array is 4 bytes wide. For those that understand, it's a pointer to an array, containing a pointer to a position in our maze. Finally, the level drawing routine needs to be updated to use memory like this too. Once again, just working our way through the memory 1 byte at a time. So let's run that and see what happens. Wow, so much quicker at 3.82 seconds, whereas the arrays it took 6.74, almost twice as fast. And now for the part that really makes it shine, let's compile it. Wow, less than half a second. That's 3 times faster than the previous compiled version. Now I know some of you may have found that concept a little bit difficult. If you're used to languages like C or C++, then pointers are a very common thing. And you can see the speed advantages we gain here. But that's the last I'm going to talk about that, so if your head's hurting, don't worry. The next thing we need to do is make this look a little nicer. I actually want to draw the map using tiles rather than just solid white boxes, and I'd like to give the map a nice edge too. So I've designed this set of tiles which represents every possible edge that our map could generate, and updated the code to add a new procedure called Tile Maze. The job of this procedure is to work out how to apply the tiles you've just seen to create the walls within the maze. The first section of code scans through every square within the maze, and if there's no floor there, it gets the floor status from the surrounding pixels. If any of them are set, or a special flag, inside, is set to true, then we write 2 to our new map. We'll use the number 2 to represent a wall, as we know the square we're currently on has nothing in it, but one of the ones around us does. If the square we're on does have something in it, then we'll write a 1 to indicate floor, and make a note that we're now inside. We then check the 4 diagonals from this square, and if any of them are empty, then they must be walls too. There is a way of optimising this algorithm further. At this point, we now have data about where the empty areas are, the floor areas and the walls. But that doesn't tell us what we want to render, so we need to scan this new data again. Some of you are thinking, well, this could be done easily using a load of if commands here and there to work out which tile to show based on what's around. But I've got a much simpler method. The order of the tiles in that graphic is actually quite important. If I write it out again with the indexes starting at 0, you can see it runs to 15, a total of 16 combinations. Now, if underneath I write their index in binary vertically, can you see a pattern yet? Well, when bit 0 is set, it should connect to a wall to the left. Bit 1, and it should connect to the wall on the right. Bit 2, and it should connect to a wall above. And finally, bit 3 should connect to a wall below. Following so far? So if we go back to the code, and for each square we get the status of the surrounding pixels, and if they contain a wall, then we set the corresponding bit in the tile variable, and that's the calculation done. Finally, we save that value back to the memory, remembering that our first tile actually starts at 1, not 0. I've also stored the number 100 to mean floor, and we'll come back to that later. Now on to our drawing routine, and it's surprisingly simple now. We just need to paste the tile number we've stored in memory. So let's have a look at that. Now, just for completeness sake, I'm going to render the floor in a different colour, and it's not quite as simple as you'd imagine. Given the design of the tiles that I'm using, if you just fill the squares that represent the floor, you end up with gaps like this. There's several ways we could fix this, but the simplest is just to take a 2-pass approach, drawing the floor first and making them slightly larger, and then drawing the walls over the top. Perfect! Not a bad start. Now this is a long way from any kind of game, but I thought you might find it interesting. The concept could easily be adapted to create multiple linking mazes or floors. You could even extend this into the 3rd dimension if you wanted to. Now I've taken this further by adding extra procedures to create more internal walls with gates and keys, as well as some different graphics more suited to the game I'm creating. So what is this game? Well, you'll have to wait out for the next video to find out. So, click that subscribe button and hit that notification bell so you don't miss it. Thanks for watching, and I'll see you in the next one.